Okay, we are now on hyperbolas. So hyperbolas are kind of like ellipses. They're what's called a conic section. And the definition for a hyperbola is the set of all points x and y in a plane. The difference is whose distances from two distinct fixed points called foci is a positive constant. See the figure, okay. So this differs from an ellipse because instead of looking at difference for an ellipse, we look at the sum. So here's a picture. So you have these two focal points, two foci, one focus. And instead of the sum of the two distances to a point on the ellipse, for a hyperbola, the difference in the two. So the distance from, and this is one part of the hyperbola, and this is another one, depending upon whether D2 is greater than D1 or D2 is less than D1. So if I were to, let's just draw a picture here. Let's just look at these lengths. So this is D2, and this is D1. And if we were to take those like this, the hard part is going to be getting them to align without me changing the length. So I'm not sure if I can do that. So that probably, yeah, see, if I do that, it's going to change the length. Anyway, if I took one and I subtracted the length of the other, I get a shorter length. And the same thing is true here. If I go to another point on the ellipse, I go from this focus to the point on the ellipse, and notice they're both longer, but the difference between the two has to be a constant. So that's the kind of the official definition of an ellipse. When we plot ellipses, we tend not to use that fact. We tend to find the vertices of the hyperbola just like we found the vertices of an ellipse, and we draw a box or a rectangle that helps us draw the hyperbola, and they're based on the equation being in standard form, and it looks very similar to the standard form for an ellipse, but instead of having x squared plus y squared of some form, you have x squared minus y squared or y squared minus x squared. So there's a difference between the squared terms. Now here's some terminology. So what you have is you have this transverse x-axis, and it's kind of like the major axis in an ellipse. You have the center, which is determined the same way that you found the center of an ellipse from the standard form. These are called branches. You'll have two branches for a hyperbola. And then the dimensions, you've got the distance from the center to the vertex as being a, just like you did with an ellipse. But the focal point is actually outside, or not the focal point, but the focal point or the focus is outside the vertex, whereas for the ellipse, the focal point was between the center and the vertex, so they get superposed here or transposed. And there's also a distance in this case the y direction, which would be equivalent to b in the ellipse, and that the b and the a allow us to draw a rectangle, and then by drawing lines between the corners of the rectangle and extending them, we can create asymptotes that help us draw in the remainder of the hyperbola. And again, depending upon which is bigger, a or b, well, which one's positive and which one's negative, it depends whether the hyperbola is oriented this way or whether it's oriented this way. The actual magnitudes of a and b relative to each other just affect the aspect ratio of the box. The thing that determines whether the hyperbola looks something like this or whether it looks something like this depends upon whether you have x squared minus y squared form or y squared minus x squared, which we'll see in a minute. So it's a little more complicated than an ellipse. So this is the standard form for an ellipse, and it looks very similar to the standard form for a hyperbola. Notice we've got two forms. We've got x squared, and then you got a negative sign y squared. Here we have y squared minus x squared. We always have the right-hand side being positive 1. So whatever we have to divide through by to make the right-hand side positive 1, that will determine which one of these is positive or negative. They're always different signs. And from this, you can find the vertices. So the vertices are always in the direction of the positive term. So in this case, x is the positive term, positive sign out here. So that goes with a goes with that. If you have y being the positive term, then a goes with that. And in terms of drawing this rectangle to help us guide how to draw the hyperbola, this number a here goes with the x dimension, and this number b goes with the y dimension. Here a goes with the x dimension, y dimension, and here b goes with the x dimension. Now we use this a in the direction of the positive term to define the vertices of the hyperbola. So let me go back to this picture here. So we know the center from h and k, or k and h and k, x and y, and then you can move to the right so many units, a units, to the left so many units. This is, you can see how here the transverse axis is horizontal, and they show here the transverse axis is horizontal. So this would be the standard form for this type of hyperbola, whereas the second standard form would be the one with the red curve. Let's see what it's in. The foci are c units from the center. So C in this case is larger than both A, well, it's larger than A. C is the focal point. It goes out here further. And you can use this relationship. So for a hyperbola, c squared is equal to a squared plus b squared. That's why c squared is always greater than a squared. It's also greater than b squared. Now, if the center of the hyperbola is the origin, then you have a simplified form of the standard equation, just like we did for the ellipse. So here the center is 0, 0, which is the origin. Because x is positive, we have a horizontal transverse axis. Here y squared is positive, so we have a vertical transverse axis. And here you can see, using the standard form, again this has x squared over a squared, so we have a horizontal transverse axis. The center is h comma k. If you move, so since it's horizontal, you're going to move a units to the left to get the vertex and a units to the right to get the vertex. Then you can move c units to the left to get the focus, and c units to the right to get the focal point. And like I said, there's you can move b in this direction to then draw a rectangle. So let's just look at an example. So we can let's start with the simple one. Let's say we have x squared over 25 minus y squared over 16 is equal to 1. So this has a horizontal transverse axis. the center is 0, 0. A is equal to 5, the square root of 25. B is equal to 4. And C squared equals A squared plus B squared. So that's 25 plus 16, which is 41. So C equals the square root of 41. And now we'll convert that to decimal notation, because we need to do that to print. So it's going to be 6.40. So let's see how we plot this thing. Let's get a piece of graph paper. So we're going to set up our normal standard scaling. So the center is going to be 0, 0. So just same thing as the ellipse. Now the transverse axis is horizontal, and we're going to move 5 units either side of the center. So you go 1, 2, 3, 4, 5. So let's use a different color. 1, 2, 3, 4, 5. That's the vertex. 1, 2, 3, 4, 5. Go the other direction. So these are vertices. Now if we go 6.4 units, so 5, 6, 6.4, those are going to be the focal points of it. And then finally, we're going to go 4 units in the other direction, which in this case is the y direction. 1, 2, 3, 4. And you go 1, 2, 3, 4. So just like we did with the ellipse, we're going to draw a rectangle, and it's going to be a horizontal line going through this point, which is on the non-transverse axis. And you could do the same thing over here. You go through the vertex, not through the focus points. Focus. Okay, so now what the heck do you do with this? And we're going to do it graphically, but we'll end up talking about the equations. So you draw a line diagonal through the center from one corner of this rectangle to the other, and then you'd extend them out to the edges of the graph, and then you can do it the other direction. So we'll start here at this corner, go through the center to the other corner, then keep going. Let's do the same thing on the other side. Now with a piece of paper you just need a ruler, and you can, once you've drawn the rectangle, everything's fine. Okay, so those are going to use us to guide to do the asymptote. Now the curve is going this way because x squared is positive. And you start at the vertex on either side, and then you smoothly go towards the asymptote. When you get close to this asymptote, what an asymptote means, it's something that you approach but you never equal. The same thing happens over here. You go out side down, and then once you get close to the wall, you start to say, oh, I'm getting a little too close, so let's bend but never cross this thing. And the same thing applies over here. So you'd start at the vertex, and you would go sideways until you start to get near that asymptote, and then you would keep drawing it like that. And you can start at the asymptote and then kind of work your way towards the vertex. And there you go. That's how it works. Now, let's say, so what's going on here? Well, the distance from here to this line back to the other focal point. So if I take this distance and I subtract this distance, you get some number. And all of these points that are on this red line have the same difference between the long section and the short section. But as far as drawing it, you really just need the vertices, these boxes, to draw the asymptotes and have this curve approach the asymptote starting the vertex. Now let's, what would happen if I had, instead of having x squared over 25 minus y squared over 16, what if I had y squared over 16 minus x squared over 25? So all that I've done is just make the x squared negative and the y squared positive. Now in this case, a is 4 and b is 5. And the a goes with the y distance, so I still go up 4 units in the y direction, down 4 units in the y direction, and I still go to the right 5 units in the x direction, 5 units in the other direction. So I still have the same rectangle. The vertex now, instead of being here, comes over there. And the focal point is now is still the square root of 41, 16 plus 25. So if I do that, it was 6.3 something units, 6.4 units. So what I would do is I go up here. This is 1, 2, 3, 4, 5, 6, 6.4. Be right there, and this would go 4, 5, 6, 6 point down the negative direction. So this particular curve would look like this. So as far as drawing the asymptotes, because the 25 still goes with the x and 16 still goes with the y, we still have the same box, we still have the same asymptotes, except we approach them from this direction. So the transverse axis here would be the vertical direction. For the previous case, where I had them the other way around, here you have a horizontal transverse axis. Okay, so let's look at another problem. Let's have the center not be equal to the origin. So we got x minus 2 divided by, let's say, 16, and y plus 2 squared divided by 9 equals 0, and I got to have a subtraction. I forgot a negative here. So from the sign, I have a horizontal transverse axis. Now, the transverse axis is associated with the x direction. So A, in this case, is 4, and B is equal to 3, square root of 16, square root of 9. C is equal to the square root of 16 plus 9, which is 20, square root of 25, which is 5. So that's C in this case. So I have everything I need. I have the center is 2 comma negative 2. So it's x minus h and y minus k. So h is positive 2 and k is negative 2. So let's go ahead and pull out a piece of graph paper. So again, we're going to put in our standard scaling. Okay, so what we do first, we plot the center. The center is 2, negative 2. Next is we take this distance 4, square root of 16, and that's in the x direction. So we go 4 units, 1, 2, 3, 4, in the x direction from the center, 1, 2, 3, 4, in the x direction from the center to both sides. The center is in between the two vertices. Now the focal points are along this transverse axis. So what we go is we go 5 units. So you get 1, 2, 3, 4, 5. Again, the focal points are outside of the vertices. The focal points, again, don't help us plot this thing. What we need is these 2 points, and then we go the opposite direction, whatever B units is. 1, 2, 3, and 1, 2, 3. And we make a rectangle to go through these 4 points individually. Let me just shift this thing around a little bit. So that is the square. Now with an ellipse, we draw it inside the square, but for a hyperbola, we draw these diagonal lines through the diagonals of through the corners of the opposite sides of this. Okay. Now again, in this case, this is greater than that. Well, this is positive. This being greater than that means that this rectangle is elongated in the x direction compared to the y direction. The negative sign here, positive sign there, means that I have a horizontal transverse axis. So we start at the vertex here and we draw it up and then approach go horizontally, not horizontally, but we approach the asymptote. Once we get there, we start, as we go further along, we'll approach that. And the same thing applies over here. So you come down, go through this line, and like that. Okay. So that's this equation. Now let's do the opposite again. So if, instead of having okay, so what if we had y squared over 9 minus, it's not y squared, it's whatever, y plus 2 squared over 9. Okay. Y plus 2 squared over 9 minus x squared minus 2 squared, x minus 2 squared over 16 equals 1. So now the negative is associated with the x squared and the positive with the y squared. But 16 is still matched up with x, so I still plot the center at 2 comma negative 2. I still go 4 units in the x direction. Now these points now would not be vertices anymore. These would just be points on the non-transverse axis. Now, because y squared is positive, you're going to have a vertical transverse axis. So the focal points are going to go still 5 units. So the 1, 2, 3, 4, 5 here, and 1, 2, 3, 4, 5 down there. So those are the foci. We start here at this. Now this is the vertices along the transverse axis, and then it comes over here and then approaches this asymptote and goes to the left and does the same thing. Approaches this asymptote, and here you come from this asymptote down through this point and then go over here. So we never go inside the box. So in the case of an ellipse, we're thinking inside the box, and when we do the hyperbola, we're thinking outside the box. We do have this one additional guide, which are these diagonal lines, which are asymptotes, so that's convenient. Okay, so now what we need to do is we need to show you how you go from something that's not in standard form. We've gone from standard form to plotting it. If you have something like the following, 9x squared minus y squared minus 36x minus 6y plus 18 equals 0. So you'll notice you have a positive x squared term and a negative y squared term. Now you can't immediately know that the final form of this equation in standard form is going to have a positive x squared and then negative y squared. It'll depend upon what happens to the constants. If this ends up being equal to a negative number, then we'll have to divide everything by a negative number, so the signs will change, so you can't always rely upon the original signs. Okay, so same way we did with the ellipses, we group the two terms together that involve x. We group the two terms together that involve y. We'll go ahead and take the constant term, move it to the other side. So a positive 18 becomes negative 18. Next thing you do is you factor out whatever constants in front of the x squared and y squared, just factoring out of the two terms that involve x or y. So 9 divided by 9 is 1. That's always the easy one. And then you take negative 36 divided by 9, which would be negative 4. Leave some space. Here we're going to factor out a negative 1. So I'm going to put the negative sign out front. So you'll get y squared. Negative y squared becomes negative the quantity of y squared. And if you divide negative 6 by negative 1, you'll get positive. So it becomes positive 6y. Leave some space. Keep that constant on the right-hand side. Okay, now, same thing, just completing the square. Take negative 4, divide by 2, square it. So you get negative 2 squared, or 4. So we add 4, but we're really adding 9 times 4, which is 36. So let's go ahead and add 36 to both sides. And here we take 6 divided by 2 squared, which is 3 squared, which is 9, so we add 9. But notice the negative sign, so we're really subtracting 9 at this point. If this had a number like negative 2 out front, we'd be subtracting negative 18, but in this case it's just negative. So we're subtracting 9, so we have to subtract 9 from both sides to balance that out. Okay, you take the coefficient out front, you make that into a complete square. So you take this number, negative 2, x minus 2 squared is that. Then you have negative 1 basically times y plus 3 quantity squared. So I'm going to take this number and add it to y. And then you add all these numbers together, which will be negative 18, negative 27, so you end up with 9 on the right hand side. Now because this is a positive 9, the signs are going to stay the same as original. Final step, well, next to final step is we divide both sides by whatever constant you have on the right hand side, because you want to get 1 there. So divide every term by 9. So here we get 1, so you'll get x squared, x minus 2 squared divided by 1. Then we'll subtract y plus 3 squared divided by 9, 9 over 1. Here we had 9 over 9. And that's equal to 1. So I can go ahead and take the 1 off of there. I just wanted to show you where that 1 becomes the denominator of this thing. So now it's in standard form. So we're going to have a horizontal transverse axis, and that's because x is positive. This term is positive. This one's negative. A is 1. The square root of 1 is 1. B is 3. Square root of 9 is 3. And c squared is equal to 3 squared plus 1 squared, which is 10. So t equals the square root of 10. And the square root of 10 is 3.16. Okay, so we have A, B, C. We have the center. So let's write that down. The center is 2, negative 3. Okay, so we have everything we need to know now. And we can plot the function. Okay, again, I'm going to use the standard scaling. Okay, so we start at the center. So we're going to go 2, negative 3. So there's a center. In the x direction, I move 1 unit either way. In the y direction, I go 3 units. 1, 2, 3. 1, 2, 3. And it's a horizontal transverse axis, so that means that the vertices and the foci are this direction. So this 3.16 is going to be over here. So I go 1, 2, 3.16. I go 1, 2, 3.16. So those are my foci. So then we draw a rectangle that is made up of these 4 line segments that go through the red and the blue, like that. But again, we're thinking outside the box here, so we're going to draw this diagonal from this corner to the other corner, extend it out, do the same thing here, do it again the other direction. So we'll start here, go through that one, and click on that, go the other direction. Okay. So we have this horizontal transverse axis, so it's going to go flare out this way. And you start at the vertex, one vertex, and be outside the box, and then go up and approach the asymptote, and you go down and approach the asymptote. Same thing here, you start at the vertex, go up towards the asymptote, and then down towards the asymptote. And I think the further away the focal point is from the vertex, relatively speaking, compared to the center, I think the flatter these things become. Okay, let's do another one. So we've got 16y squared minus x squared plus 2x plus 64y plus 63 equals 0. So we group the y terms together. 16y squared plus 64y. Group the x squared terms together, and move the constant to the right hand side. So we're going to factor out the 16. 16 times y squared, divide 64 by 16, you get 4y, leave a space, factor out the negative sign, so you get x squared minus 2x, leave some space, negative 63. Then we take 4 divided by 2, square it, that's 2 squared, which is 4, so we add 4, but we're really adding 16 times 4, which is 64. So we're adding 64 here, so we have to add 64 to the right hand side. Next, we take negative 2, divide by 2, square it. It's negative 1 squared, which is 1. So we add 1. So we're let's just finish it, but you'll see why I went in just a second. So we're really subtracting 1. So if we subtract 1, you get 0 on this side, which means it's not really a hyperbola anymore. So let's pick a different number here. So I'm going to pick plus 10, just so we have something to draw. So if we put plus 10 here, this becomes minus 10. So you have minus 10. And when you add all those three things together, you get 54, and minus 1 is 53. So this is 53. These three together. So what you end up with is 16 times x, or pardon me, y plus 2 squared plus 2 minus x minus 1, that number, squared is equal to 53. And because I just picked that number out, this, it's not going to be nice. The numbers are going to be a little fishy, but we can still do the problem. It's still going to work out. So you divide both sides by 53. So you get that. And then what we would do is we would rewrite this as y plus 2 squared over 53 over 16. Instead of 16 over 53, we take the reciprocal of that. Then you have minus x minus 1 squared over 53 equals 1. So we have y-axis is the and well, we'll say it's a vertical transverse axis instead of a horizontal. Vertical transverse axis. So now it's going to look this way, go this way. So a squared is this, well, is equal to 53 over 16. So a is the square root of that, and we're just going to come up with a decimal number. 53 divided by 16. Take the square root of that. We get 1.82. And b is going to be the square root of 53. So that is equal to 53 square root. You get 7.3. And c squared is equal to 1.82 squared plus 7.3 squared. 1.82 squared plus 7.3 squared. Take the square root, you get 7.5. this is equal to 56.6. So you take the square root of that, you get 7.52. Okay. And finally, we can explicitly say what the center is. I'll do it down here. The center is -2, 1 from here, -2, 1. Okay, so let's get a piece of graph paper. Okay, so plot the center. -2, 1. So there's the center. The y-axis is the vertical direction is the direction of the transverse axis. But the actual distance we go is equal to a, which is 1.82. So we go 1.82, 1.82. So that gives us part of the box. B goes the other direction, 7.3. So we go 1, 2, 3, 4, 5, 6, 7.3. 1, 2, 3, 4, 5, 6, 7.3. Now the foci goes 7.52, and it's always in the direction of the transverse axis, so we actually go 7.52 up and down. 1, 2, 3, 4, 5, 6, 7.5. I guess I should use a different color, blue. So there's blue. And you go down from the center, 1, 2, 3, 4, 5, 6, 7.52. And then we're going to draw the rectangle which connects these points, the inner points, not these ones that are way out there. I'll line these in just a second once I get them about in the right place. Okay, so this one's going to move over a little bit. This one's going to move up a little bit. I'm going to make it a little shorter. This one move over to the right a little bit. This one looks pretty good. So now we draw our diagonal lines from corner to opposite corner. Okay. And because the vertical direction is the transverse axis, we start here, this point. These two are foci. These two are vertices. These two are foci. These 2 points just help me define this rectangle. So it's a really flat hyperbola. It's going to start there at that vertex, and it's going to come over here, do the same thing. Same thing down here. We start at this vertex, we go over to the horizontally, we do the same thing here. Now, and the only thing would be different if this were positive and this were negative is you'd have the hyperbola would go over here. Okay, so here, let's just kind of review where we are. So if you look at this equation over here, x minus h squared over a squared minus the quantity y minus k squared over b squared equals 1. Because x squared is positive, we have a horizontal transverse axis. The center is associated with h and k. Now from the center, if you go take the h coordinate, which is the x coordinate, and you go in the x direction, -c units, that would be the location of the focal point here, and you go the other direction, the same distance, so it's h plus c. That would give you the location of the focal point. Now if I wanted to know the vertices, these are the vertices, and so for the vertices, the coordinates would be h minus a, comma k, and the location of this would be h plus a comma k. So all of these things have the same k value, which is the y coordinate. Now this is the other situation where the y part is positive and the x part is negative. So in that case you have a vertical transverse axis. In this case h is constant and the y coordinate changes. So again these are the two focal points. The coordinate of the vertex is going to be h comma k plus a again, because a always goes with the positive thing. So you can't say a is x or b is y. It's a goes with the positive term. And down here the vertex, the coordinates of the vertex would be h comma k minus a. Now you'll notice in neither one of these does b show up. So that requires you to look at these asymptotes, which we have been drawing in just by drawing the box, by going, b units this way and b units that way and making this box, and then drawing diagonals from the corners of these two boxes, from two corners of the box, the matching opposite corners. Now here it actually gives you the equation for the line. If you wanted to use a graphing program to plot the diagonals without drawing the box, you could do that. And the equation, they're both y is a function of x, because that's the way we write lines, equation for lines. But the difference is that because for a horizontal transverse axis, the a corresponds to the x part and b corresponds to the y part, then we have b over a. But when you have a vertical transverse axis, then you switch them, because now a here, which is associated with this one here, a goes with the y part and b goes with the x part. So it's always the y over the x, just because it's a slope. Slope is y over change in y over change in x. But all the other things stay the same. And and what they're basically doing here is they're using the point slope form of the linear equation. So you got y minus y1 is equal to m times x minus x1. And the point that we're going through, both of these lines go through the center of the box, the center of the hyperbola. So that's why this one is k, which is the y coordinate of the center, and why this one is h, because that's the x coordinate of the center of the so all we've done here is take the point slope form of the linear equation, use k and h instead of y1 and x1, and then solve for y without multiplying everything out. I'm going to show you a program that I have just to demonstrate how this works. So let's go back to one of the ones that we've already plotted. We'll pick one that had easier things to use here. So let's choose this one. So here's the actual graph, and this was the equation in standard form. So the question is, what are the equations for the asymptotes? So this is a case where we have x is positive and y is negative. So this is a horizontal transverse axis. So we have h is equal to 2 and k is equal to -3. So we need those two things. We have a is equal to 1 and b is equal to 3. So that says that the equations for the asymptotes, let me find the equation so I don't have to get off this page. Okay, so we're going to use the one with a horizontal transverse axis, which is y is equal to k plus or minus b over a times x minus h. Okay, so let's plug in what we know. K is -3 plus or minus b, which is 3, over a, which is 1, times x minus h. H is 2. Make sure I got all that right. K, -3, plus or minus a. Actually, I got those the wrong way around, didn't I? Or did I? Well, it's b over a, sorry. So b is 3, a is 1. So that is correct. X minus h, h is 2. Okay. So let's just clean this up a little bit. So you get y is equal to -3 plus or minus 3 times x minus 2. So there are two lines. We have y is equal to -3 plus 3 times x minus 2, and we have y is equal to -3 minus 3 times x minus 2. So we're going to plot these two lines, and we're going to plot this hyperbola using the graphic program that I'm just going to pull up here. So it's just a free thing I found online. And we're going to do a two-dimensional plot. And we're going to put an equation. So first we're going to put in what we called an implicit equation. And that's what this parabola, this hyperbola is this equation. So let's put that in there. So it's going to be x minus 2 squared divided by 1 minus y, go find the rest of the equation here, minus the quantity y plus 3 squared divided by 9 equals 1. And let me make sure that I'm setting the scale here correctly before I plot this thing. So let's look at our graph that goes along with this. So you can see it goes down to -6. So I probably need to make this a little bit, change the scale, which I can't do right yet. But what I'm going to do is I'm going to zoom out so I can. The problem what happens is when you do that, you lose some of the detail. So what I need to do is graph it again. It's still not. So let me edit this and then try it. Okay. So what I'm going to do is I'm going to get rid of this, delete, and then do it again. Because for some reason it's. Now that I have it zoomed out, I'll do the same. Just redo what I just. Oh. Okay, let's zoom out before we plot anything. Okay. So now we're zoom out. Now we can put an equation in. So we're going to do an implicit equation, and the equation was x. Already forgotten it again. X minus 2. X minus 2 squared divided by 1 minus y plus 3, I believe, plus 3 squared divided by 9 equals 1. Okay, so there it is. So you can see the the hyperbola. Now what we can do is we can add another equation. So we're going to do this as an explicit equation because it's going to be y equals something. Here they have f of x. So, and let me move, well, I can't move it down yet. Just realized it's getting out of the screen. Okay, so the equations were the equations for the lines, which are these down here. So it's -3 plus 3 times x minus 2. See if that's right. -3 plus 3 times x minus 2. Okay. So I'm going to say okay. That's one line, and then we'll do it again. Another explicit equation. It's going to be negative 3 minus 3 times x minus 2. So that's the second equation, negative 3 minus 3, x minus 2. If I graph that, let's say OK. There you go. And what I could also do is draw the box. So you can see how these functions, the red function, which is the hyperbola, approach the blue lines, which are the asymptotes. Now I think I should be able to put in a line segment, and I just have to put in the corner values for this box. So it's going to be 1, 0, and 3, 0. Put that in there. 1, 0. Actually, go the other way around. 1, 0, 3, 0. Say OK. Okay, I don't see it. Oh, it's right here. You can't see because it's on the axis. Okay, let's try the next one. So we're going to do a segment. And in this case, we'll go from 3, 0 to 3, negative 6. 3, 0, 3, negative 6. Say OK. So there's that vertical part. You can see how this aligns with the vertex. Then we're going to go from 3, 0 to actually 3, negative 6 to 1, negative 6. So it's going to be 3, negative 6, 1, negative 6. So that gives me the horizontal part here. So there's the part of the box. And then we're going to go from 1, negative 6 to 1, 0. 1, negative 6 to 1, 0. So that's going to be a vertical line. So there you go. So we can't see this segment because it corresponds to the x-axis, but that's my box. And the box is defined by this point, this point, this point, and that point, which is what we plot. So normally what we do is we plot the center, which is where these two lines cross. Because this is a horizontal transverse axis, we go from the center plus A and minus A, which was A was 1. And then we go from here in the y direction plus 3 units to get this point, and minus 3 units in the y direction to get that point. So when we draw lines through, vertical lines through these 2 points and horizontal lines through those 2 points, you create this box, which allows you then to connect the 2 corners of the box to give you the appropriate asymptote for this particular function. So that's the whole concept. If you want to look from a mathematical perspective and you want to be able to plot the lines, you can use these equations to plot the lines. But what I'm going to ask you to be able to do is plot the center, depending upon whether it's the transverse axis is vertical or the transverse axis is horizontal, to move either, in the case of vertical, you go up A units and down A units from the center, and you go to the left and the right B units. That allows you to draw this rectangle. Then you can draw a diagonal through the opposite corners of the rectangle. That ends up with these asymptotes. And then you can start your hyperbola at this point, the midpoint of each one of these, the midpoint of these boxes, and then draw them so they approach the asymptote. And here you can see it as far as what's going on here. So you've got your box, you've got, in this case, we have a horizontal transverse axis. You've got this asymptotic line going diagonally. You've got this asymptotic line going diagonally. They cross at the center of the hyperbola. In this case, this point, well, here they're finally showing you how you get the coordinates of the other part of the box. Instead of going this way, h stays, well, actually k stays constant. Here you'd have h minus a, and here you'd have h plus a. If you go the other direction, you have k plus b and k minus b. Okay, so that's the whole idea there. The last fact we're going to talk about is eccentricity, and you define eccentricity very similarly as you did with ellipses. So it's going to be E is equal to C over A. Remember, C is the distance from the center to a focus, and A is the distance from the center to the vertex. So if this is much greater than 1, then you have a high eccentricity, and it's less symmetric. So the closer this is to 1, the more symmetric it is, meaning it moves up in the x and y direction fairly evenly. In this case, it's moving up much more quickly in the y direction than it is in the x direction. And that can be quantified using the eccentricity. So this is an example of a large eccentricity. This is one that's closer to 1, and it's stretched out, actually goes in the other direction. So I should say, so I don't know, notice how this one's kind of crowded in this direction. This one's crowded in this direction. So these are both with a horizontal transverse axis. So if you're given hyperbolas in standard form, you should be able to plot them. If you're given them not in standard form, you have to get them into standard form. The last skill here is give you some details about the vertices and the focus, and you're supposed to come up with the standard form. So here's an example. Let's say the vertices are 0 plus or minus 2. The foci are 0 plus or minus 4. So what's the equation in standard form? Well, let's get a piece of graph paper and plot these. Kind of think our way through this thing visually. Okay, so the vertices are 0 plus 2, 0 minus 2. The foci are 0 plus or minus 4, so you get that point and you get that point. So you can see these are all aligned. So from just this observation, we can say we have a horizontal transverse axis. So what does that mean? Well, it means that A is going to be equal to 2, because the distance from the center to the vertices is 2. So A is 2. We know that C, which is the distance from the center to the focal points, is 4. And we know that C squared is equal to A squared plus B squared. So if we want to solve for B, B squared equals C squared minus A squared. So that's 4 squared minus 2 squared, which is 16 minus 4, which is 12. So B is the square root of 12. So that would, let's find the square root of 12 in decimal form. Okay, square root of 12 is 3.46. So the b is going to go vertical direction. 1, 2, 3, 3.46 that way. 1, 2, 3, 3.46 that way. Now you could draw a box now, and I'll kind of rough it in, and then I'll move things around. Okay, that looks pretty good. And then we can draw our diagonal for the asymptotes. Okay, and then we can finally draw it in. So we're going to start here at this vertex, and then draw them as they go out, approach the asymptote. Okay, so that's the actual graph. But what else can we say? Well, you notice the center here is at the origin, and that's if you take the midpoint of these two vertices, or the midpoint of the two focal points, you get 0, 0, because it's right aligned along symmetrically along there. So we know that h equals 0 and k equals 0. So finally, the answer is going to be x minus 0, which is just x. So we get x squared divided by a squared. A is 4 minus y squared divided by 12, because b is the square root of 12, and that is equal to 1. So that's the standard form of that equation, that given information. Okay. Let's do another one. So we got the foci are 0 plus or minus 8. I think all these first set are the ones that are centered around the origin. So let's plot this thing. Okay, so x equals 0, y equals 8, plus or minus 8. So we go up here. There's that, and there's that. So first thing we can say is that we have a vertical transverse axis. So we know the focal points have to be somewhere along this y-axis between these 2 points. The focal points are always outside, so the vertex is somewhere in here. Now it says that the equation for the asymptote is y equals plus or minus 4x. So there's no the y-intercept is 0. And what you do is you have a slope of plus 4. So it would look something like that. And you extend that through the center. You might say, well, how do you know it's in the center? Well, because midway between the two focal points is the center. So it is centered around the origin. And then you could do the same thing going the other direction, negative 4. So that would go to here, to there, to there. Okay. So now what do I do? Well, if you look at the equations for the asymptotes, that'll help us figure this out a little bit more. So if we look at the equations for the asymptotes, and this is a vertical transverse axis, so the one we're going to use is y is equal to k plus or minus a over b times x minus h. Well, in our case, k is 0 and h is 0, so we get plus or minus a over b times x. So what we know is a over b, and a goes with the y direction. So a over b is 4. We also know that what else do we know? We know that c squared is equal to a squared plus b squared. And we have c squared. We have c, 64, right? So c is 8. So you get that. So we got 2 equations and 2 unknowns. So the best thing to do is to take this equation and say a is equal to 4b, and then you can substitute in here 64 is equal to a is 4b, so we get 4b squared plus b squared. So 64 is equal to 16b squared plus b squared, or 64 is equal to 17b squared. B is equal to b squared is equal to 64 over 17. And a squared is, what is a squared equal to? Well, a squared is equal to 64 minus b squared. So I'd have b squared here. So that's 64 minus 64 over 17. So we get a, yeah, it's more difficult than I thought it was going to be, but in terms of, so 64 times 17, you get 1088 minus 64 over 17. So 1088 minus 64 divided by 17. Yeah, this is a prime number. You can't simplify it, so it just comes out to be 1024 over 17. So that's equal to b squared, or a squared. Let's see if that's true. Let's just double check it here. So if you take this squared plus this, so a squared plus b squared equals, if you add these two together, you get 1088 over 17, and that 1088 divided by 17 is 64, and the square root of 64 is 8. So now that we have a and b, you can put in standard form. So it's going to be y, because we have a vertical transverse axis, minus 0, because it's the center, is the origin. So you have y divided by a squared, which is 1024 over 17. This is squared, minus x squared divided by 64 over 17 equals 1. And lo and behold, that's the right answer. Okay, so let's kind of review that, because it was kind of a... So what we did was we said, we plotted the focal points, the foci. If you take the midpoint, you get the center. you could draw the asymptotes, but that really didn't help until we came to the equation for the asymptote lines. Because the center was the center of the hyperbola was 0, 0, it's simplified down to that. And we know that this ratio, y over x change, was equal to 4 from the slope here. So we knew a over b had to be 4, but that's one equation and two unknowns. But from the location of the foci, we knew what C was. C was 8. And we knew that c squared equals a squared plus b squared. So we had two equations once we plugged c, the known c value, in there. So c was 8, so you get 8 squared is 64. So we got these two equations. I solved for a. I could have solved for b as well, but I solved for a from this equation and substituted it into this equation. So a squared plus b squared became 4b quantity squared plus b squared. 4 squared is 16. B squared is b squared. So you get 16 plus 1, which is 17. So we get 64 equals 17b squared, or if you divide by 17, you get b squared equals 64 over 17. That's where the b value came. Then I plug that back in to this equation here to find, if I solve this equation for a squared is equal to 64 minus b squared. So I had 64 minus b squared. There's b squared. If you do the fractions, you get 1,024 over 17. That's a prime number. Well, 17 is a prime number, and you can't divide 1024 by 17. So this turns out to be a squared. Now I didn't plot a or b for this because they were just asking for the equation. But once I had b squared and a squared, and I know the center, then that's all I need to put the equation in standard form. Okay. Now let's do another few here. So, okay, this one, vertices. Now, for the test, I'm just going to ask you to draw these. You won't have to actually do these kinds of problems, but I do want to work them out just for you guys who are a little better at this kind of stuff, that you see the reasoning associated with it, as well as I'm going to assign a few homework problems like this. Okay, so let's plot these things out and see where we're going. Just looking at the numbers is not really going to help me too much. It's just too confusing. Okay, vertices are 4, 1 and 4, 9. So there's the vertices. The foci are 4, 0 and 4, 10. So hopefully you see that it's a vertical transverse axis. We know that C is equal to what? Well, where's the center? Well, if you go 1, 2, 3, 4, 5, 6, 7, 8, so there's 8 between those, so just go 4, 1, 2, 3, 4. So there's your center. So let's write the coordinates of the center. Center is the point 4, 5. And then we have that c squared is equal to a squared plus b squared. Now here we have c is the distance from the center to each foci. So 1, 2, 3, 4, 5. So c is 5. A is the location, the distance from the center to the vertices. So that's 1, 2, 3, 4. So all we need is b squared to get everything we need to put this in standard form, because we get the center, we just need a and b. So if we solve this for b squared, it's going to be c squared minus a squared. So c is 5, minus a, which is 4. So that's 25 minus 16, which is 9. So b squared is 9. Now, I could say b is 3, which is true. But to put this in standard form, I don't really need b. What I have is I'm going to have x. Well, let's see. Do we do x first or y first? Well, because it's a vertical transverse axis, I put y first. So it's going to be y minus 5 squared divided by a, which is 4. Well, a is 4, so a squared is 16, minus x minus 4, quantity squared, because I have a center here at x equals 4. And then I go the b direction, the x direction, b squared, and the right-hand side is 1. So that's how that kind of thing works. So the best thing to do is to plot the points, the information you're given, and then use the fact that the center is between the vertices and the foci. Use the fact that c squared equals a squared plus b squared. Use the fact that if you have the equation for the asymptote, that the slope is either a over b or b over a. So all those are little things that take a little more practice to actually be able to understand, but it's... So I think I'm going to stop there, and I'm going to give you some homework. So I'm going to come up with some homework problems for you to practice all of the things that we've talked about so far.